Time flows. It moves forward, always forward, carrying us with it from past through present into future, like passengers on an unstoppable river. This isn't philosophy or theory. It's what we feel, what we know with such certainty that questioning it seems absurd. You remember eating breakfast this morning, that memory safely tucked in the past, fixed and unchangeable. Right now, in this present moment, you're reading these words, experiencing them as they happen. And tomorrow, the future stretches ahead, uncertain and unwritten, waiting for you to move into it. Past, present, future. 3 distinct territories of time, as real and separate as the rooms in your house. But what if I told you that this fundamental experience, this seemingly obvious truth about reality, is an illusion? Not a simple misunderstanding, but an elaborate construction your brain creates, moment by moment, to make sense of a universe where time doesn't actually flow at all. Think about your morning. You woke up, got out of bed, maybe made coffee or tea, and went about your routine. Each action followed the previous one in a sequence that felt natural, inevitable. The morning led to afternoon. Afternoon will lead to evening. This forward motion through time is so deeply woven into the fabric of your experience that it's nearly impossible to imagine it any other way. When you remember yesterday, those events feel behind you, receding into the past. When you think about next week, those possibilities feel ahead of you, approaching from the future. The present, this very second, feels like the razor's edge between what was and what will be. The only moment that truly exists. The only time that's real. We build our entire lives around this experience. We learn from the past, make decisions in the present, and plan for the future. We grieve for time lost and anticipate time to come. We age, we change. We watch seasons cycle and years accumulate. Every clock we've ever built, every calendar we've ever consulted, reinforces this understanding. Time is something that passes, something that moves, something that flows from yesterday into today into tomorrow. But here's where things get strange, where the comfortable certainty of our daily experience begins to crack. Scientists have been studying time for centuries, using increasingly sophisticated tools and theories, and what they've discovered doesn't match what we feel at all. According to our best understanding of physics, the flow of time, that undeniable forward motion you experience every waking second, doesn't exist in any fundamental way. It's not written into the laws of nature. It's not woven into the fabric of the universe. The division between past, present, and future that seems so obvious, so real, appears to be something our minds create, not something the cosmos provides. This isn't some fringe theory or wild speculation. This is the conclusion that emerges from Einstein's relativity, from our understanding of thermodynamics, from quantum mechanics. The structure of reality, as physics reveals it, is profoundly different from the structure of our experience. And reconciling these two pictures, what we feel versus what the equations tell us, remains one of the deepest puzzles in all of science. Let's start with something simple and familiar. Your memory of eating breakfast this morning. That memory exists now in your brain as a pattern of neural connections, a configuration of matter and energy in the present moment. The breakfast itself, the actual event, is gone. It no longer exists in any physical sense. You can't touch it, can't return to it, can't change it. It's past, finished, done. Or is it? When you think about tomorrow's plans, those plans exist as thoughts, as neural patterns in your brain right now. The actual tomorrow, the events that will happen, don't exist yet. They're in the future, waiting to occur. Or are they? And what about right now, this very instant you're experiencing? How long is now? A second? A millisecond? The moment you try to pin it down, to say, this is now, that moment has already slipped into the past. The present seems to be constantly vanishing, an impossibly thin boundary between what was and what will be. It's always already gone by the time you notice it. These simple observations have puzzled philosophers for millennia. Augustine of Hippo, way back in the 4th century, wrestled with the paradox of time in his Confessions. If the past no longer exists and the future doesn't exist yet, and the present has no duration, then when exactly does time exist? His conclusion was both profound and disturbing. Time might be entirely in our minds, a feature of consciousness rather than a feature of the external world. For most of human history, we didn't have the tools to probe deeper into this mystery. We relied on our direct experience, and our experience told us unambiguously that time flows forward. Philosophers argued about the nature of time, about whether it was absolute or relative, about whether it existed independently of the events that happen in it. But no one seriously questioned the basic experience of temporal flow. How could they? To question the flow of time felt like questioning the existence of the ground beneath your feet. Then came the scientific revolution. Galileo, Newton, and others began describing motion mathematically, creating equations that could predict where objects would be at different times. Newton, in particular, believed in what he called absolute time, a cosmic clock that ticked steadily forward, the same for everyone, everywhere in the universe. Time was like an invisible river, flowing at a constant rate, carrying all events with it. This matched our experience perfectly. Time flowed, Newton said, without relation to anything external. It just flowed, period. That was its nature. But Newton's absolute time came with an interesting property. His equations of motion worked just as well forward as backward. If you filmed a planet orbiting the sun and played the film in reverse, the reversed motion would still obey Newton's laws perfectly. The mathematics didn't prefer one direction of time over the other. This was puzzling, but it didn't seem to threaten the obvious truth that time actually flows forward in reality, even if the equations couldn't tell the difference. Then came Einstein, and everything changed. In 1905, Albert Einstein published his special theory of relativity, and in that theory, Newton's absolute time died. Einstein showed that time isn't absolute or universal. It's relative. It depends on motion. Two observers moving at different speeds will disagree about how much time passes between events. They'll even disagree about which events happen first. There's no universal now spanning the cosmos. Each observer has their own time, their own present moment. This wasn't just theoretical speculation. Einstein arrived at these conclusions by thinking carefully about how we measure time and simultaneity. Imagine you're standing in the middle of a moving train car and lightning strikes both ends simultaneously from your perspective. You see both flashes at the same instant because you're equidistant from both ends. But someone standing on the platform watching the train pass sees something different. From their perspective, the light from the front of the train reaches their eyes before the light from the back because the train is moving toward one flash and away from the other. Since light travels at a constant speed for all observers, a key principle Einstein built into his theory. The platform observer concludes that the two strikes weren't simultaneous. They happened at different times. Who's right? Both are. There's no absolute fact about whether the strikes were simultaneous. It depends on your reference frame, your state of motion. This is the relativity of simultaneity, and it completely undermines the Newtonian picture of a universal present moment spanning all of space. But the implications go even further. Moving clocks run slower than stationary ones. This is called time dilation, and it's been confirmed by countless experiments. Atomic clocks flown around the world on airplanes tick slower than identical clocks that stay on the ground, by exactly the amount Einstein's equations predict. GPS satellites have to account for time dilation, or they'd accumulate errors and give you wrong directions. Particles created in particle accelerators live longer when they're moving fast, decaying more slowly in their own reference frame than in the lab's reference frame. All of this is real, measured, verified physics. Time is not absolute. It genuinely runs at different rates for different observers depending on their motion. A twin who travels to a distant star at near light speed and returns will have aged less than their stay-at-home sibling. This is the famous twin paradox, though it's not really a paradox. It's a straightforward consequence of time dilation. Then, a decade later, Einstein extended these ideas to include gravity in his general theory of relativity. He showed that gravity isn't a force in the traditional sense, but a curvature of space-time itself. Mass and energy warp the geometry of space-time, and objects moving through this warped geometry follow curved paths we perceive as gravitational attraction. But gravity also affects time. Time runs slower in stronger gravitational fields. A clock on the ground floor of a building ticks slower than a clock on the top floor because it's deeper in Earth's gravitational field. The effect is tiny for everyday heights, but it's measurable with sufficiently precise atomic clocks. And near very massive objects like black holes, time dilation becomes extreme. If you could hover just outside a black hole's event horizon, you'd see the rest of the universe speeding up, stars forming and dying, galaxies colliding, the cosmos evolving at an accelerated rate. Meanwhile, observers far from the black hole would see your time crawling to a near standstill. This was shocking enough, but a few years later, Einstein's former teacher, Hermann Minkowski, realized something even more radical. The equations of special relativity worked best when you stopped thinking about space and time as separate things and started thinking about them as a unified four-dimensional structure: space-time. In this picture, the 3 dimensions of space plus 1 dimension of time combine into a single geometric object, and the events that make up the history of the universe are all laid out in this 4-dimensional space-time like points on a map. Minkowski famously declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This was revolutionary. For thousands of years, space and time had been thought of as separate arenas in which things happen. Now they were revealed to be aspects of a single, unified structure. Space and time aren't separate containers. They're interwoven dimensions of one geometric whole. But here's the thing that shakes our everyday experience to its core. In the mathematics of space-time, there's no preferred moment called now. The past, present, and future all exist together, all at once, as part of the same four-dimensional structure. Your birth exists somewhere in space-time. Your death exists somewhere in space-time. The moment you're experiencing right now, reading these words, exists in space-time. But so does every other moment of your life, and of everyone else's life, and of the entire history of the universe. They all exist together, laid out in the four-dimensional geometry of space-time. This picture is often called the block universe, and it challenges everything we think we know about the nature of time. In the block universe, time doesn't flow, it doesn't move, it just is. All moments exist equally. The future is already there, just as real as the past. The past hasn't disappeared, it's still there. And the present isn't special, it's just one slice among many slices of the space-time block. Imagine a book. The book has many pages, and each page exists simultaneously as part of the complete book. You might read the book page by page, experiencing the story as unfolding in sequence. But the entire story exists all at once in the physical object of the book. Page 100 exists just as much as page 1, even when you're reading page 1. The block universe suggests that time is something like this. All moments exist together, and you, as a conscious being, might experience them sequentially, but they're all equally real, all equally there. If this is true, if the block universe picture is correct, then the flow of time is an illusion. Not an illusion in the sense that time doesn't exist, but an illusion in the sense that it doesn't flow. The passage of time, the movement from past to future, the special status of the present moment, these are features of our experience, not features of the universe. This is profoundly disorienting. It goes against everything we feel. When you remember your childhood, it feels like those events are in the past, behind you, gone. When you anticipate tomorrow, it feels like those events haven't happened yet, that they're ahead of you, still to come. The present moment feels special, unique, the only time that's actually real. But according to the block universe picture, this is all a kind of cognitive illusion, a story your brain tells to organize your experience. And yet, despite how strange and counterintuitive this sounds, it's the picture that emerges most naturally from our best physics. Relativity doesn't give us any reason to think the present moment is special. The equations treat all times equally. The geometry of space-time includes past, present, and future in the same mathematical structure. If you want to insist that only the present exists, or that the past exists but the future doesn't, you have to add something extra to the equations, something that isn't there in the basic theory. Some physicists and philosophers have tried to do exactly that, to modify the block universe picture to preserve something closer to our common sense intuition that the future isn't yet real. There's the growing block theory, which says that the past and present exist, but the future is genuinely not yet there. As time passes, new slices of reality come into existence, adding to the growing block of what has happened. This feels more aligned with our experience. The past is fixed, the present is happening, and the future is open. But the growing block theory has its own problems. For one thing, it's hard to make it compatible with relativity. Remember, different observers moving at different speeds disagree about which events are in the present. If new slices of reality are coming into existence at the present moment, which present moment? Yours? Mine? The universe doesn't come with a preferred reference frame, so there's no natural way to say which observer's present is the real growing edge of the block. There's also presentism, the view that only the present exists. The past is gone, the future isn't yet here, and only now is real. This matches our experience most closely, but it's even harder to reconcile with relativity for the same reasons. Plus, if only the present exists, what does that mean for objects that are moving? Their present includes events that are in my future. Do those events exist or not? The questions multiply, the contradictions pile up. So we're left with a puzzle. Our experience tells us with absolute conviction that time flows from past through present into future, that the present moment is special and unique, that the past is gone and the future is yet to come. But our best physics tells us that time doesn't work this way, that all moments exist together in the four-dimensional block of space-time, that the flow of time is something our minds add to a reality that doesn't actually flow. This isn't just an abstract philosophical puzzle. It touches the core of what it means to be human, to be conscious, to experience the world. If time doesn't really flow, why does it feel so powerfully like it does? What is this experience we call now? Why do we remember the past and not the future? Why does cause always seem to precede effect? These aren't just questions for physics. They're questions about consciousness, about memory, about the nature of mind and its relationship to the physical world. And here's what makes this mystery so deep, so fascinating. We can't simply dismiss our experience as wrong. Our experience of time is real. The feeling that time flows is genuine, not a simple mistake. But we also can't dismiss what physics tells us. The equations of relativity have been tested thousands of times, in thousands of different ways, and they work. GPS satellites have to correct for relativistic time dilation, or they'd give you wrong directions. Particle accelerators produce particles that live longer when moving fast, just as relativity predicts. The block universe might feel wrong, but it's built on a foundation of experimental evidence. So we're caught between two truths: the truth of our experience and the truth of our equations. Time flows and time doesn't flow. The present is special and the present isn't special. Past and future are different, and past and future exist equally in space-time. How do we make sense of this contradiction? The answer, it turns out, requires us to dig deeper into multiple different aspects of physics and neuroscience. We need to understand entropy, the second law of thermodynamics, and why some processes in nature have a preferred direction even though the fundamental laws don't. We need to understand quantum mechanics and how it treats time. We need to understand how the brain constructs the experience of now, how memory works, how consciousness emerges from neural activity. And we need to understand why, even in a block universe where all moments exist together, we experience them as flowing in one direction only. This journey will take us to some strange places. We'll discover that the forward arrow of time might emerge from something as simple as the universe starting in a low entropy state. we'll learn that your memory of the past is intimately connected to the second law of thermodynamics. We'll find that the brain doesn't experience the present moment directly. It's always slightly behind, always predicting, always constructing a coherent narrative from delayed and fragmentary information. We'll confront the possibility that consciousness itself, with its vivid sense of now, might be the only place where time truly flows, even if that flow is an emergent property rather than a fundamental feature of reality. Before we can understand why time doesn't flow the way we think, we need to understand what science has discovered about why it seems to flow at all. And that requires us to first explore one of the most important concepts in all of physics: entropy, and the arrow of time it creates. Drop a coffee mug on the floor and it shatters into dozens of pieces. Those pieces never spontaneously jump back together to reform the mug. Leave a hot cup of tea sitting on a table and it cools to room temperature. It never spontaneously absorbs heat from the cooler air to become hot again. These simple observations point to one of the deepest principles in physics: the arrow of time. Unlike the block universe, which treats all moments as equally real and doesn't prefer any direction of time, our everyday experience is filled with processes that only go one way. Eggs scramble but never unscramble. Ice melts but never spontaneously freezes from room temperature water. Buildings crumble with time. They don't grow more organized. This one-way direction of events is so universal, so obvious, that we rarely stop to ask, why? The answer lies in a concept called entropy. Entropy is often described as disorder, though that's not quite accurate. More precisely, entropy is a measure of the number of possible microscopic arrangements that correspond to the same macroscopic state. Let me explain what that means. Think about that coffee mug again. When it's intact, sitting on your desk, all the molecules that make up the ceramic are arranged in a very specific configuration. There's basically one way for the mug to be a functioning mug. Its molecules need to be arranged in the mug shape. But once you drop it and it shatters, those same molecules can be arranged in countless different ways and still count as broken mug. The pieces could land over here or over there. They could be slightly different sizes. They could be oriented differently. There are millions upon millions of different microscopic arrangements that all look macroscopically like broken mug. In physics terms, the intact mug is a low entropy state because there are very few arrangements of molecules that correspond to it. The broken mug is a high entropy state because there are many, many arrangements of molecules that correspond to it. And here's the crucial point. Systems naturally evolve from low entropy states to high entropy states. Why? Simply because there are more high entropy states to evolve into. It's a matter of probability. If you randomly shuffle the molecules, you're far more likely to end up with a high entropy configuration than a low entropy one, just because there are so many more high entropy configurations available. To put this in perspective, imagine you have a deck of cards. There's basically one arrangement that counts as perfectly ordered. All cards in sequence, sorted by suit. But there are billions upon billions of arrangements that count as shuffled or random. If you shuffle the deck, the probability of ending up with the perfectly ordered arrangement is vanishingly small, not because there's a force preventing order, but simply because there are so many more disordered arrangements possible. The deck naturally evolves toward disorder, not through any active process, but through sheer probability. Or think about a gas in a container. If you somehow managed to get all the gas molecules into one corner of the container, with the rest of the container empty, that would be an incredibly low entropy state. There's basically one way for all the molecules to be in that specific corner. But once you let them go, they spread out to fill the entire container. Why? Because there are vastly more ways for the molecules to be spread throughout the whole space than for them all to be clustered in one corner. Each molecule moves randomly, bouncing off others in the walls, and purely by chance, the molecules end up distributed throughout the available volume. The remarkable thing is that if you could somehow track every single molecule and reverse all their velocities, making them all move backward along their exact paths, the gas would indeed flow back into the corner. The laws of motion are time-symmetric, after all, but the probability of this happening by chance is essentially zero. It would require an incredibly specific coordination of all the molecules' motions, a coordination that random bouncing will never produce. This is the second law of thermodynamics, one of the most fundamental principles in all of physics. It states that in any closed system, entropy tends to increase over time. Or, more carefully, entropy tends toward a maximum. It never decreases in a closed system. This law is not absolute in the sense that it's theoretically impossible for entropy to decrease. It's statistically incredibly unlikely. The probability of a broken mug spontaneously reassembling is not zero, but it's so close to zero that it effectively never happens. You could wait trillions of years and never see it. The astronomer Arthur Eddington, who helped confirm Einstein's general relativity through eclipse observations, said of the second law, "If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." He understood that this law is so fundamental, so universally observed, that violating it would require overturning everything we know about physics. This increase in entropy is what gives us the arrow of time. It's why events seem to have a preferred direction, why things age and decay and fall apart. When you see a video of a mug breaking, you immediately know which direction time is flowing. Forward. If you see a video of a broken mug spontaneously reassembling, you know the video is being played backward. The second law of thermodynamics is what allows you to tell past from future just by looking at whether entropy is increasing or decreasing. But here's what's strange. The fundamental laws of physics that govern individual molecules, the laws of motion, the laws of quantum mechanics, the laws of electromagnetism, these are all time-symmetric. If you take any microscopic process and reverse the direction of time, the reversed process is also physically possible. Individual molecules don't care which way time flows. They can bounce forward or backward with equal ease. This creates a profound puzzle. How does time asymmetry at the macroscopic level emerge from time-symmetric laws at the microscopic level? How does the arrow of time arise from physics that doesn't have an arrow? The answer seems to be initial conditions. The second law of thermodynamics tells us that entropy tends to increase from any given moment forward. But it doesn't tell us why entropy was lower in the past. That's not a law of nature. That's a fact about the initial state of the universe. For reasons we don't fully understand, the universe began in an extremely low entropy state. The Big Bang itself was a configuration of extraordinary order, with all the matter and energy of the universe compressed into an incredibly small, hot, dense state that had remarkably low entropy given its energy. From that low entropy beginning, the universe has been evolving toward higher entropy states ever since. Stars form, burn, and die. Galaxies collide and merge. Black holes form and evaporate. Heat spreads out until everything reaches equilibrium. This is the cosmological arrow of time, pointing from the ordered beginning toward the disordered future. And this cosmological arrow is intimately connected to every other arrow of time we experience. Consider memory. You remember the past but not the future. Why? Because memory is a physical process, and like all physical processes, it creates entropy. When your brain encodes a memory, it creates correlations between your neurons and external events. This correlation is a kind of organization, a low entropy structure. But creating that structure requires energy, generates heat, and increases the total entropy of the universe. The direction of memory's arrow matches the direction of entropy's arrow. You can only remember events that happened when the universe had lower entropy than it does now. You can't remember the future because the future is in the direction of increasing entropy, and your brain can't create correlations with events that haven't yet created the necessary physical traces. This connection between memory and entropy is profound. It means that your ability to remember the past is not some special feature of consciousness or biology. It's a consequence of thermodynamics. Any physical system that stores information about its past interactions is subject to the same constraint. Your computer's hard drive remembers past data, not future data, for the same fundamental reason your brain does. The psychological arrow of time, our sense that time flows from past to future, might be entirely a consequence of the thermodynamic arrow. We experience time as flowing forward because we remember the past and not the future. And we remember the past because the universe started in a low entropy state. If the universe had started in a high entropy state, or if entropy were decreasing instead of increasing, we might remember the future and forget the past, and time would seem to flow backward. Stephen Hawking explored this idea in his book, A Brief History of Time. He pointed out that the thermodynamic arrow, the psychological arrow, and the cosmological arrow all point in the same direction, from the organized past toward the disordered future. And he argued that this is no coincidence. The psychological arrow has to align with the thermodynamic arrow, because brains are thermodynamic systems. We couldn't function, couldn't remember, couldn't exist as conscious beings if entropy were decreasing. There's even a causal arrow of time. Causes precede their effects. This seems obvious. You can't have an effect before its cause. But why not? What in the laws of physics prevents backward causation? The answer, again, seems to be entropy. When one event causes another, correlations increase between the cause and the effect. The effect carries information about the cause, and increasing correlations means increasing entropy. so causal relationships naturally point in the direction of entropy increase, which is forward in time. Consider a simple example. You drop a stone into a still pond, and ripples spread outward. The stone is the cause. The ripples are the effect. Information about the stone's impact travels outward with the ripples. Now imagine the time-reversed version. Ripples converge from all directions on a single point, perfectly timed to eject a stone from the water. This would require an enormous coincidence, an extraordinary organization of the water molecules. It would be a massive decrease in entropy. That's why we never see it happen. Even light and sound follow an arrow of time. Waves expand outward from their sources. You never see light converging from all directions onto a light bulb to make it glow. Why? Because the expanding wave represents entropy increase, information spreading out, becoming less concentrated. A converging wave would be entropy decrease, requiring precise coordination of trillions of photons. All these arrows, thermodynamic, psychological, causal, electromagnetic, point the same way. They're all consequences of the same underlying fact. The universe started in a low entropy state and has been evolving toward higher entropy ever since. But this raises a deeper question. Why did the universe start in a low entropy state? This is known as the past hypothesis, and it's one of the great unsolved problems in physics. We don't have a good explanation for it. The Big Bang itself, as far as we understand it, doesn't require low initial entropy. The equations of general relativity that describe the expanding universe work just as well with high initial entropy. So why was the beginning special? Why was it organized rather than random? Some physicists speculate that the answer might lie in quantum gravity, in a theory that unifies general relativity and quantum mechanics. Perhaps the very early universe, at scales smaller than the Planck length, behaves in ways that naturally produce low entropy initial conditions. But we don't have that theory yet, so this is pure speculation. Others suggest that we might be asking the wrong question. Perhaps the universe goes through cycles of expansion and contraction, and what we call the Big Bang was just one phase in an eternal series. Or perhaps there are countless universes in a multiverse, each with different initial conditions, and we necessarily find ourselves in one with low initial entropy, because only such universes can support observers like us. This is a version of the anthropic principle. We observe what we observe because if things were different, we wouldn't be here to observe anything. But regardless of why the universe started in a low entropy state, the fact that it did is crucial for understanding the arrow of time. Without that special beginning, there would be no preferred direction. Eggs would be just as likely to unscramble as to scramble. Time would be symmetric. The universe would be a featureless equilibrium with no interesting structures, no life, no consciousness. The increase of entropy is also what will determine the ultimate fate of the universe. If the universe continues expanding forever, as current evidence suggests, then eventually all stars will burn out. All matter will decay into its simplest forms. All energy will spread out until it's uniformly distributed. The universe will reach maximum entropy, a state of perfect equilibrium where nothing interesting can ever happen again. This is sometimes called the heat death of the universe. In that far future state, there would be no arrow of time. With no entropy gradient, no difference between past and future, time would effectively lose its direction. Any observers still around, if such a thing were even possible in a maximum entropy universe, would experience no flow of time. They'd have no memories, no causal relationships, no sense that moments follow each other in sequence. Time would still exist in the sense that events would still have temporal locations in spacetime, but it wouldn't flow. It wouldn't point anywhere. This connection between entropy and the flow of time is one of the most beautiful and troubling discoveries in all of physics. Beautiful because it explains so much. Why we age, why we remember the past, why causes precede effects, why the universe has a history. Troubling because it suggests that the flow of time, which feels so fundamental, so real, is actually a contingent feature of our particular cosmic epoch. In a maximum entropy universe, or in a universe that started in a high entropy state, there would be no flow. Time would just be, the way space just is. No motion, no passage, no direction. And yet, even with all this understanding, we haven't fully explained the subjective experience of time's flow. We've explained why entropy increases, why memories point backward, why causes precede effects. But we haven't explained why it feels like time is flowing, why there's a vivid sense of now that seems to move forward through moments. That's a different kind of mystery, one that takes us from thermodynamics to neuroscience, from physics to the study of consciousness. The arrow of time tells us that there is a direction to events, a pattern to how things unfold. But it doesn't tell us why we experience that direction as a flow, as motion, as the passage of a present moment through successive instants. To understand that, we need to understand how the brain creates the experience of time. And that's where things get even stranger. Let's return to Einstein and what his theories really tell us about the structure of time. Because if we're going to understand why time doesn't flow the way we think, we need to understand what modern physics says time actually is. In 1905, when Einstein published his special theory of relativity, he was trying to solve a specific problem about light and motion. But the implications of his solution were far more radical than anyone expected. Einstein showed that time is not absolute, it's relative. It depends on your state of motion. Imagine two observers, Alice and Bob. Alice is on Earth. Bob is on a spaceship moving past Earth at close to the speed of light. They both observe the same events, say, a flash of light when Bob's spaceship passes Alice, but they disagree about when other events happen. Events that Alice sees as simultaneous, happening at the same time. Bob sees as happening at different times. Events that Bob sees as simultaneous, Alice sees in sequence. This isn't just a difference in perception, like two people with different perspectives on a sculpture. This is a difference in the actual structure of space-time itself. There's no absolute fact about whether two distant events happen at the same time. It depends on your reference frame. There's no universal now that spans the cosmos. Your now and my now, if we're moving relative to each other, are different three-dimensional slices through the four-dimensional space-time. This leads to what's called the relativity of simultaneity, and its implications are profound. If there's no universal now, then there's no objective present moment. Your present includes events that are in my future. My present includes events that are in your past. The neat division between past, present, and future breaks down completely when you account for relative motion. Hermann Minkowski, one of Einstein's teachers, realized that the mathematics of relativity became much clearer if you stopped thinking about space and time separately and instead thought about them as a unified four-dimensional continuum called spacetime. In this view, every event that happens has four coordinates: 3 spatial coordinates telling you where it is, and 1 temporal coordinate telling you when it is. These 4 coordinates together specify a point in spacetime, what physicists call an event. The trajectory of an object through spacetime is called its world line. Your world line is the path you trace through the four-dimensional spacetime as you move through space and time. It starts at your birth and ends at your death, and every moment of your life is a different point along that world line. The world line of someone else crosses yours when you meet them. The world line of a photon is a line of light-speed motion through the space-time structure. Now here's the key insight. In the mathematics of relativity, all these world lines, all these events, all these moments exist together in the space-time geometry. The equations don't distinguish between past, present, and future. They treat all times on the same footing, just as they treat all spatial locations on the same footing. Just as every point in space exists, every moment in time exists. They're all part of the same four-dimensional structure. This is the block universe, past, present, and future, all laid out together, all equally real, all existing in the same sense that different spatial locations exist. Your birth and your death are both events in space-time, and they both exist, just at different temporal coordinates. The entire history of the universe, from the Big Bang to the ultimate heat death, is all there in the space-time block. To visualize this, imagine a book again. Each page of the book represents a three-dimensional snapshot of the universe at a particular time. The first page is the Big Bang. The last page, infinitely far away, is the end of time. Every page in between is a different moment, a different configuration of matter and energy throughout space. Now the complete book, with all its pages bound together, is space-time. Every page exists, every moment is there. You, as a conscious observer, might experience these pages sequentially, reading through the book one page at a time. But the book itself contains all the pages simultaneously. This means something profound and strange. According to the block universe, the moment of your birth exists just as much as the moment you're experiencing right now. Your first day of school exists. Your first heartbreak exists. Every conversation you've ever had exists. These aren't just memories, mental reconstructions of events that no longer are. They're actual events, actual regions of space-time, as real and present in a four-dimensional sense as this very moment. Similarly, your future exists. The moment of your death exists in space-time. Every decision you'll make tomorrow exists. Every experience you'll have next year exists. It's all laid out in the four-dimensional geometry, all present in the eternal now of space-time. This challenges our deepest intuitions about what exists. We naturally think that only the present exists. The past is gone, the future hasn't arrived yet. But the block universe says that's wrong. All times exist. Past and future are just directions in the four-dimensional manifold, no different in principle from north and south, east and west, up and down. Or think of it like a film. each frame of the film is a snapshot of a moment. When you watch the film, you see motion, change, things happening in sequence. The hero walks across a room, opens a door, has a conversation. But the film itself, the physical reel or digital file, contains all the frames at once. They all exist together. Frame 1 exists just as much as frame 1000. The beginning of the movie exists just as much as the end. The experience of motion comes from viewing the frames in sequence, but that doesn't mean the later frames come into existence only when you reach them. They were always there in the film. The block universe says reality is like this. All moments exist together in the four-dimensional structure of space-time. Your experience of time as flowing, as moving from past through present to future, is like your experience of watching a film. The frames don't move. You move through them, or rather, your consciousness moves through them. The flow is in your experience, not in the reality the experience is about. Consider what this means for something like the Civil War, or the construction of the pyramids, or the extinction of the dinosaurs. These events aren't gone. They exist at specific temporal coordinates in space-time. You can't access them from your current temporal location, just as you can't visit Australia without traveling through space. But they're there, as real and solid in their part of space-time as you are in yours. And think about what it means for the future. Every person who will ever live exists in space-time. Every discovery that will ever be made, every artwork that will ever be created, every child who will ever be born, they all exist at future temporal coordinates. The future isn't a blank canvas waiting to be painted. It's already there, already written, already determined, in some sense, by the total four-dimensional structure of space-time. This picture is deeply strange to think about. It means that right now, as you read these words, every moment of your past still exists somewhere in space-time. Your childhood exists. Your first day of school exists. Every conversation you've ever had exists. They're not gone. They're just at different temporal coordinates than your current moment. Similarly, every moment of your future already exists. Your death exists in space-time. Everything that will happen to you tomorrow exists. It's all out there, all laid out in the four-dimensional block. Does this mean the future is predetermined? That's a controversial question. Some philosophers argue that the block universe implies determinism. If the future already exists, then it's already fixed and you can't change it. Others argue that this is a confusion, that already exists doesn't make sense when talking about time itself. The future exists at future times, not at the present time. Saying it already exists smuggles in an illegitimate notion of absolute time. But regardless of the determinism question, the block universe picture clearly challenges our intuitive notion of the passage of a time. In the block universe, time doesn't pass. There's no universal moment moving forward through the timeline. There's no objective becoming, no events coming into existence and then receding into the past. There's just the four-dimensional structure, unchanging and eternal, containing all of space-time at once. Some physicists and philosophers have pushed back against this picture. They point out that while relativity treats all times mathematically on the same footing, that doesn't necessarily mean they're all equally real. Maybe the equations are just a useful computational tool, And the real universe has a genuine flow of time that the equations don't capture. One alternative view is presentism, which holds that only the present exists. The past is gone, the future isn't yet real, and only the current moment has being. This matches our intuitive experience very well, but it's hard to reconcile with relativity. If there's no universal now, which present is the one that exists? Different observers have different presents. Do all of them exist? Does none of them? The questions become tangled quickly. Another alternative is the growing block universe. This view says that the past and present exist, but the future doesn't. New moments are continually coming into existence at the leading edge of time, adding to the growing block of what has happened. This captures our intuition that the past is fixed, but the future is open. But again, it faces problems with relativity. Which observer's present is the growing edge? And what does it mean for new time to come into existence? Existence is supposed to be timeless. Something either exists or it doesn't. How can there be a time at which something comes to exist? These alternatives try to preserve some version of the flow of time, some sense that the present is special and the future is genuinely open. But they all struggle with the implications of relativity. The block universe, for all its strangeness, emerges naturally from the mathematics. You don't have to add anything extra to get it. It's what you get when you take relativity seriously. Einstein himself seemed comfortable with the block universe picture, though he recognized how strange it was. In a famous letter to the widow of his friend Michel Besso, written shortly before his own death, Einstein wrote, "Now he has departed from this strange world a little ahead of me. That signifies nothing. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. Only an illusion. Not that time doesn't exist, but that its division into past, present, and future is illusory. That the flow of time, the becoming, the passage, these are features of our perception, not features of the universe. Reality, Einstein seemed to believe, is the four-dimensional block. Our experience of flow is something we add to that reality. This is a hard pill to swallow. It goes against everything we feel. When someone we love dies, we don't feel like they still exist at an earlier temporal coordinate. We feel like they're gone, that they no longer exist in any sense. When we anticipate the future, we don't feel like we're thinking about something that already exists in space-time. We feel like we're thinking about something genuinely open, undecided, not yet real. But feelings, however powerful, are not always reliable guides to reality. We feel like the Earth is stationary and the sun moves across the sky, but that's not what's happening. We feel like solid objects are truly solid, but physics tells us they're mostly empty space with particles held together by forces. Our intuitions evolved to help us navigate the middle-sized world of everyday experience, not to reveal the deep structure of reality. The block universe is what you get when you follow the mathematics where it leads, and the mathematics has been tested extensively. GPS satellites wouldn't work if we didn't account for relativistic time dilation. Particle accelerators observe time dilation all the time. Gravitational time dilation has been measured with atomic clocks at different altitudes. The predictions of relativity have been confirmed over and over. So we seem to be stuck with this picture, a four-dimensional block of space-time where all moments exist together, where past and future are equally real, where time doesn't flow in any objective sense. This is what physics tells us about the structure of time. But if time doesn't flow, why does it so powerfully feel like it does? If the present moment isn't special, why does consciousness seem to have this vivid, undeniable quality of nowness? If the future already exists in space-time, why do we experience it as open and uncertain, while we experience the past as fixed and knowable? These are questions that physics alone cannot answer. They require us to understand something about consciousness, about how subjective experience emerges from physical processes. They require us to understand how the brain creates the experience of time, how neural activity gives rise to the feeling of now, how memory works and why it points backward. And they require us to confront one of the deepest mysteries in all of science: the relationship between the objective world that physics describes and the subjective world that consciousness inhabits. The block universe might be the truth about space-time, but the flowing time is the truth about experience. How do we reconcile these truths? How does the static structure of space-time give rise to the dynamic experience of temporal flow? To even begin answering these questions, we need to understand what's happening at the quantum level, where the very nature of time becomes even more mysterious. So far, we've talked about time in the context of relativity and thermodynamics, theories that deal with the large-scale structure of the universe. But there's another pillar of modern physics that has profound things to say about time: quantum mechanics. And what quantum mechanics tells us about time is, if anything, even stranger than what relativity tells us. Quantum mechanics is the theory that describes the behavior of matter and energy at the smallest scales: atoms, electrons, photons, and other fundamental particles. It's a theory that has been fantastically successful, explaining everything from the structure of atoms to the behavior of semiconductors to the properties of lasers. It's also a theory that seems to violate common sense at every turn. One of the most puzzling aspects of quantum mechanics is its relationship to time. The fundamental equations of quantum mechanics, the Schrödinger equation in non-relativistic quantum mechanics, the Dirac equation in relativistic quantum mechanics, are time-symmetric. Just like Newton's laws and Maxwell's equations, they work just as well forward as backward. If you reverse the direction of time, the equations still describe physically possible processes. But there's a catch. Quantum mechanics has a special role for measurement. When you measure a quantum system, something strange happens. Before measurement, the system exists in what's called a superposition. It's in multiple states at once, in some sense. An electron can be spinning both clockwise and counterclockwise simultaneously. A photon can be passing through two different slits at the same time. These aren't just different possibilities. The electron or photon is genuinely in both states, and this shows up in interference experiments. Then you measure the system, and the superposition collapses. The electron is found to be spinning one way or the other. The photon is detected at one slit or the other. The act of measurement forces the system to choose a definite state from all the possibilities it was in before. This collapse is not time-symmetric. It happens in one direction only. Before measurement, the system is in superposition. After measurement, it's in a definite state. You never see a system in a definite state spontaneously expand into superposition. The collapse introduces an asymmetry, an arrow of time into quantum mechanics. But here's the problem. Nobody knows what measurement really is or why it causes collapse. The measurement problem is one of the longest standing puzzles in quantum mechanics. The Schrödinger equation doesn't describe collapse. It describes smooth, deterministic, time-symmetric evolution. Collapse is something extra, something that seems to be bolted onto the theory without a clear physical mechanism. Some interpretations of quantum mechanics try to explain measurement without collapse. The many worlds interpretation says there's no collapse at all. Every possible outcome of a measurement actually occurs, but in different branches of reality. When you measure an electron's spin, the universe splits into two branches, one where you find spin up and one where you find spin down. From your perspective, in one branch, it looks like the superposition collapsed, but really both outcomes happened in different parallel universes. In the many worlds interpretation, quantum mechanics is perfectly time-symmetric. There's no collapse, just branching. But this comes at the cost of accepting that countless parallel universes are constantly being created, a price many find too high to pay. Other interpretations, like the pilot wave theory or de Broglie-Bohm mechanics, say that particles always have definite positions and properties, and the wave function just describes our knowledge of those properties. In these interpretations, there's no collapse, because there was never a real superposition to begin with. It was always just a description of possibilities, not a description of what's actually there. These debates have raged for a century, and there's still no consensus. What everyone agrees on is that quantum mechanics challenges our understanding of time in fundamental ways. Even the basic notion of when something happens gets murky in quantum mechanics. Consider the quantum Zeno effect. If you measure a quantum system frequently enough, you can effectively freeze its evolution. A radioactive atom that would normally decay within a certain time can be prevented from decaying by constantly measuring whether it's decayed. The more frequently you measure, the less likely it is to decay. It's as if the act of observation stops time for the atom. Or consider entanglement. When two particles become entangled, their properties become correlated in ways that can't be explained by any classical theory. If you measure one particle and find it spinning clockwise, the other particle, no matter how far away, will be found spinning counterclockwise. The correlations are instantaneous, faster than light, seemingly violating the principle that information can't travel faster than light. Einstein called this spooky action at a distance and thought it proved that quantum mechanics was incomplete. But experiments have shown that the correlations are real. They really do happen instantaneously, regardless of the distance between the particles. How is this possible? How can one measurement instantly affect another measurement light years away? The answer seems to be that the correlations don't involve sending information faster than light. The entangled particles don't communicate with each other. Instead, their properties are fundamentally connected in a way that transcends spatial separation. They're not two separate systems. They're one system described by a single quantum state. When you measure one particle, you're not causing the other particle to take on a certain property. You're learning about a property that was already there in the joint state of both particles. But this raises questions about time and causality. if the correlations are instantaneous, does that mean one measurement causes the other? Or are both measurements effects of a common cause in the past when the particles became entangled? Different interpretations of quantum mechanics give different answers, and experiments haven't yet been able to definitively settle the question. There's also the question of time in quantum gravity. General relativity describes gravity as the curvature of spacetime caused by mass and energy. Quantum mechanics describes matter and energy as inherently quantum, subject to uncertainty and superposition. Combining these two theories into a theory of quantum gravity has been a holy grail of physics for decades. But quantum gravity faces a fundamental problem. In general relativity, time is part of the geometry of spacetime. It can curve, stretch, dilate. In quantum mechanics, time is usually treated as a fixed background parameter, the thing with respect to which systems evolve. How do you combine a theory where time is dynamic and relative with a theory where time is absolute and external? Some approaches to quantum gravity, like loop quantum gravity, suggest that time might be emergent, that it doesn't exist at the most fundamental level, but arises as an approximation in certain regimes. At the Planck scale, the smallest possible scale of length in time, spacetime itself might be quantized, broken up into discrete chunks. Time might not be continuous, but instead made of individual instants, like frames in a film. Other approaches, like string theory and its extensions, work in higher dimensional spacetimes where our familiar 4 dimensions are just a slice of a larger structure. Time might be just one direction in a 10 or 11 dimensional manifold, no more fundamental than the extra spatial dimensions we don't directly perceive. Then there's the Wheeler-DeWitt equation, an attempt to describe the quantum state of the entire universe. This equation doesn't have a time variable. It's completely timeless. The universe, as a whole, doesn't evolve in time according to this equation. Time only emerges when you consider subsystems within the universe and how they're correlated with each other. If this is right, then time is not fundamental. It's an emergent property, something that arises from deeper, timeless physics. The flow of time, the arrow of time, the structure of past, present, and future, all of these would be secondary phenomena derived from a fundamental reality where time doesn't exist at all. This is a radical idea, and it's far from proven. But it shows how deep the mystery of time goes in quantum mechanics. We don't even know if time is fundamental or emergent. We don't know how to consistently combine quantum mechanics and general relativity. We don't know what measurement is, or why superpositions collapse. We don't know if there are many worlds or one world. We don't know if the future is determined or open. What we do know is that at the quantum level, many of our intuitions about time break down. The neat separation between cause and effect gets fuzzy. The idea of a definite present moment becomes problematic. The notion of time as a smooth, continuous flow gives way to something stranger and more subtle. And yet, for all this quantum weirdness, there's one symmetry that seems to be absolute: CPT symmetry. This stands for charge conjugation, parity reversal, and time reversal. The CPT theorem says that if you take any physical process, reverse its particles with antiparticles, charge conjugation, flip it in a mirror, parity reversal, and run it backward in time, time reversal, you get another physically possible process. Individual symmetries can be violated. Some processes violate parity, they don't look the same in a mirror. Some processes violate charge conjugation or time reversal, but the combination of all three, CPT, seems to be absolutely conserved in all known physics. This is a deep fact about the structure of physical law, and it connects to the nature of time in ways we're still trying to understand. Time reversal violation has been observed in certain particle physics processes involving the weak nuclear force. The decay of certain particles happens at slightly different rates forward and backward in time. This violation is tiny, and it's compatible with CPT symmetry because it's accompanied by violations of charge and parity symmetry. But it shows that time reversal is not an absolute symmetry of nature. Yet this violation is completely different from the thermodynamic arrow of time. The particles that exhibit time reversal violation are symmetric at the level of individual processes. Any process that violates time reversal in one direction has a time-reversed process that violates it in the opposite direction. There's no preferred overall direction. The thermodynamic arrow, on the other hand, is directional. Entropy increases in one direction of time for the whole universe. So quantum mechanics gives us several different aspects of time to think about. There's the time parameter in the Schrödinger equation, which is symmetric. There's the time asymmetric collapse of the wave function during measurement. There's the time reversal violation in weak interactions. There's the mysterious role of time in quantum gravity. And there's the question of whether time is fundamental or emergent. None of this directly tells us why we experience time as flowing. Quantum mechanics, like relativity, seems to describe a reality where time just is, where all moments exist in some sense, where the flow and passage are not part of the fundamental structure. But quantum mechanics adds new puzzles about the role of observers, about the connection between measurement and reality, about the nature of possibility and actuality. These puzzles become even more pressing when we try to connect the physics of time to the experience of time. Because ultimately, everything we know about time comes through our consciousness, through our subjective experience of moments and memories and anticipations. And that experience is created by the brain through neural processes that we're only beginning to understand. To truly understand why time doesn't flow the way we think, we need to understand how the brain creates the illusion that it does. We need to understand the neuroscience of time, the mechanisms that give rise to our sense of now, our feeling of duration, our perception of temporal order. And that's a different kind of science, one that connects physics to biology, objective reality to subjective experience. You're experiencing the present moment right now. This very second, as you read these words, you have a vivid, immediate sense of now. The past feels behind you, the future ahead, and you're poised at the razor's edge between them in this moment, this present instant. But here's something that might surprise you. That present moment you're experiencing isn't the actual present. It's the past. By the time you become conscious of anything, a sight, a sound, a thought, it's already over. The brain is always playing catch-up, constructing your experience of now from information that arrived tens or even hundreds of milliseconds ago. Think about vision. Light from the world around you enters your eyes, gets converted into electrical signals by your retina, travels along the optic nerve to your visual cortex, and then gets processed through multiple stages of neural analysis. before you become consciously aware of what you're seeing. This takes time, roughly 50 to 80 milliseconds for simple visual stimuli, and up to 200 milliseconds for more complex processing. 200 milliseconds might not sound like much, but in that time, the world has moved on. If you're watching a tennis match and a ball is traveling at 100 miles per hour, it moves more than 9 feet in 200 milliseconds. By the time you become conscious of seeing the ball at a certain location, it's already somewhere else. Your brain knows this is a problem, so it does something remarkable. It predicts. It doesn't just wait for sensory information to arrive and then construct your experience. It actively predicts what's going to happen next based on what just happened, and it uses those predictions to create your experience of the present moment. Neuroscientist Rosalind Moran and her colleagues have studied this predictive process. When an object is moving smoothly across your visual field, your brain extrapolates its trajectory forward. It essentially fills in where the object should be by the time you become conscious of it, compensating for the neural delays. This is why you can catch a ball or hit a moving target. Your brain is seeing where things are going to be, not where they were when the light hit your retina. But this predictive system sometimes makes mistakes, and those mistakes reveal how constructed our sense of now really is. In one experiment, researchers showed participants a moving object that suddenly disappeared. Brain recordings showed that for a brief moment after the object vanished, participants' brains continued to act as if the object was still there, still moving along its predicted path. The brain was so committed to its prediction that it kept seeing something that was no longer present. Similarly, when a moving object suddenly changed direction, participants' brains initially continued extrapolating along the original trajectory before catching up to reality. The brain's prediction of where the object would be took time to correct, creating a temporary mismatch between what was actually happening and what participants experienced. This might sound disturbing. Your conscious experience is running on predictions that are sometimes wrong, but it's actually brilliant. The alternative would be experiencing the world with a constant delay, always seeing where things were rather than where they are. By predicting forward, the brain creates a sense of now that's closer to the actual present, even if it's never quite there. This same predictive principle applies to all your senses. When you hear someone speaking, your brain is constantly predicting the next sound based on the patterns of speech. This is why you can understand speech even in noisy environments. Your brain fills in missing sounds based on context and prediction. It's also why you sometimes hear something different from what was actually said, when your prediction is strong enough to override the actual sensory input. Touch, too, involves prediction. When you reach out to grab something, your brain predicts how it will feel based on visual cues and past experience. This prediction shapes your actual tactile experience. Studies have shown that when predictions and sensory input mismatch, the brain can actually suppress the sensory input, favoring its own predictions about what should be happening. But here's what's really fascinating. The brain doesn't just predict external events. It predicts its own future states. Your sense of intending to do something, of making a decision, of initiating an action. These experiences are constructed by the brain predicting what it's about to do. The famous experiments by Benjamin Libet showed that brain activity associated with a decision to move occurs up to half a second before people report consciously deciding to move. This has led to intense debates about free will and the nature of conscious intention. If the brain starts preparing to act before you consciously decide to act, does that mean your conscious decision is an illusion? Or is conscious decision just the later stage of a process that starts unconsciously? These questions remain contentious, but what's clear is that the brain's construction of your sense of agency, of being the one who decides and acts, is temporally complex and involves multiple stages of processing. The construction of the present moment also involves something called temporal binding, the brain's ability to link events that happen at slightly different times into a unified experience. Vision and sound, for instance, are processed at different speeds. Visual information from your eyes reaches consciousness faster than auditory information from your ears. And yet, when you watch someone speak, their lip movements and their words seem perfectly synchronized. Why? Because the brain adjusts. It waits for slower signals to catch up and binds them together into a coherent experience where everything seems to happen at once. This binding happens within what's sometimes called the specious present, a window of a few hundred milliseconds within which events are experienced as simultaneous, even though they're objectively sequential. The philosopher William James coined the term specious present to capture the idea that our sense of now isn't an instantaneous point, but a brief duration, a moving window of awareness that includes the immediate past, what we just experienced, and the immediate future, what we're anticipating. This window is typically estimated to be somewhere between a half second and 3 seconds, though it varies depending on what you're attending to. Within this window, you experience events as happening now, as part of the present moment. Outside this window, events feel either in the past or in the future. This is why you can experience a melody as a unified whole, even though the notes occur in sequence. They all fall within your specious present, but you can't hold a whole symphony in your immediate awareness. It extends beyond the window, and you experience it as unfolding over time. This window of nowness is not fixed. It can expand or contract depending on your state of mind. In flow states, when you're deeply absorbed in an activity, the specious present can seem to expand, making time feel like it's moving more slowly or even stopping. In moments of fear or surprise, time can seem to slow down because your brain is processing more information per unit of physical time, creating more memories and thus giving you the subjective impression that more time has passed. The psychologist Mihaly Csikszentmihalyi studied flow states extensively and found that in these states, people often report losing their sense of time altogether. Hours can pass in what feels like minutes. The normal flow of time seems to suspend. This suggests that our everyday sense of time's passage is maintained by a certain level of self-monitoring, a tracking of how long things take and how much has happened. In flow, that self-monitoring shuts down, and with it, the strong sense of time passing. Athletes often report similar experiences. A basketball player in the zone might say the game seemed to slow down, that they had all the time in the world to make decisions that objectively happened in split seconds. A race car driver might describe seeing everything in slow motion during a crash. These aren't just metaphors. They reflect genuine alterations in subjective time perception. Studies have shown that time perception can be manipulated in laboratory settings. Present subjects with a frightening or novel stimulus, and they typically overestimate its duration compared to neutral stimuli of the same length. The emotional salience of the stimulus causes the brain to encode more information about it, creating more memories, and those richer memories make the event feel like it lasted longer. In one famous study, researchers had people bungee jump while trying to estimate how long they were in free fall. The jumpers consistently overestimated the duration. Their own falls seemed to last longer than they actually did. But when they watched video of other people's falls, they accurately estimated the duration. Fear and adrenaline, it seems, make time subjectively expand, but only for your own experiences, not for observed events. On the other hand, when you're bored or waiting for something, time seems to drag. The same 10 minutes in a waiting room can feel much longer than 10 minutes engaged in enjoyable activity. This isn't because your brain's clock is actually running slower. It's because you're paying attention to time itself, creating more temporal markers in your experience, and thus feeling each minute more acutely. When you keep checking a clock, each check creates a memory, a timestamp, and the accumulation of these timestamps makes you feel like more time has passed than when you're absorbed in activity and not monitoring time. There's even evidence that as we age, our subjective experience of time speeds up. Many people report that years seem to last forever in childhood but fly by in adulthood. One explanation is that when you're young, almost everything you experience is novel, creating rich memories and making time feel extended. As you age and fall into routines, fewer things are novel, fewer rich memories are created, and time seems to pass more quickly. Another explanation involves proportional time. When you're 10 years old, 1 year represents 10% of your entire life, a huge fraction. When you're 50, 1 year is only 2% of your life, a much smaller fraction. So each year feels proportionally shorter as you age, even though the objective duration is the same. Neuroscientists have identified several brain regions involved in time perception. The cerebellum seems to be important for timing intervals in the range of milliseconds to seconds, particularly for motor timing, knowing when to initiate movements to catch objects or play musical rhythms. Damage to the cerebellum can impair your ability to accurately time movements, making you clumsy or unable to maintain steady rhythms. The basal ganglia, particularly the striatum, appears to be involved in interval timing on the scale of seconds to minutes. This is the kind of timing you use when you're trying to judge whether a minute has passed or when you're waiting for a light to turn green. Patients with Parkinson's disease, which affects the basal ganglia, often have impaired time perception in this range, underestimating how much time has passed. And the prefrontal cortex seems to be crucial for working memory aspects of time perception, keeping track of temporal order, planning future actions, and maintaining a coherent sense of temporal continuity. This is the part of the brain that lets you remember that you did task A before task B, that event X happened yesterday, and event Y will happen tomorrow. Damage to the prefrontal cortex can disrupt this temporal organization, making it hard to maintain a coherent narrative of your life across time. But there's no single clock in the brain. no master timekeeper that tracks time absolutely. Instead, timing is distributed across multiple neural systems, each adapted to different scales and types of temporal processing. Some neurons fire at regular intervals and could serve as basic oscillators, biological metronomes that tick at a consistent rate. Networks of neurons can create more complex timing patterns through their interactions, with some neurons exciting others and some inhibiting, creating rhythmic patterns of activity that could encode temporal information. And the overall dynamics of brain activity, the ebb and flow of neural rhythms at different frequencies, contributes to the sense of time passing. Interestingly, these neural mechanisms are not perfectly accurate or consistent. Time perception is subject to all kinds of distortions and illusions. The oddball effect, for instance, occurs when an unexpected stimulus in a series of repeated stimuli seems to last longer than the others, even though all stimuli are actually the same duration. Your brain allocates more processing to surprising events, creating more memories, and this makes them seem to occupy more time. There's also the stopped clock illusion. When you look at a clock and the second hand seems to pause for longer than a second before moving again. This happens because when your eyes move, your brain suppresses visual input during the movement itself to prevent blurring. Then, once your eyes land on the clock, your brain retrospectively fills in what you saw during the eye movement with the image you're seeing now. This makes the first second you see seem longer than it actually is. These illusions reveal something important. Your experience of time is constructed, malleable, subject to the vagaries of neural processing. It's not a direct readout of some objective temporal reality. It's a model, a simulation that your brain creates to help you navigate the world. And this brings us to a crucial point. If your experience of the present moment is constructed, delayed, predictive, and subject to illusions, then what does this mean for the flow of time? Is the flowing present something real that the brain is tracking, or is it something the brain is creating? The evidence strongly suggests it's the latter. The flow of time, the sense that you're moving forward through moments, the feeling that now is special and distinct from past and future. These are features of your conscious experience, and conscious experience is something the brain constructs. The brain takes the four-dimensional space-time described by physics, where all moments exist together, and creates from it a three-dimensional space, evolving through one-dimensional time, with a moving now that feels vivid and real. But why would the brain do this? Why construct a sense of flow when the underlying reality might not flow at all? The answer seems to be that a flowing present moment is useful. It helps you organize your experience, distinguish between what's already happened and what hasn't, plan for the future, and learn from the past. If you experienced all moments simultaneously as they exist in the block universe, you couldn't function. You need to track temporal order to understand causality, to know that eating food causes you to feel full, not the other way around. You need to distinguish past from future to make decisions. Should I do this action? Well, I can't do an action in the past. I can only do it in the future. So my decisions must concern future actions. The sense of now, of a present moment distinct from past and future, is a cognitive tool. It's how the brain organizes the blooming, buzzing confusion of sensory input and memory and prediction into a coherent narrative of experience. And because this organization happens unconsciously, automatically, constantly, it feels utterly natural and real. You don't experience it as a construction. You experience it as simply how things are. But it is a construction. And recognizing this helps us understand why the flow of time, despite feeling so real, doesn't appear in the fundamental equations of physics. It's not because physics is missing something, though it might be. It's because the flow is in our minds, in how we process information, in the architecture of consciousness. This doesn't make the flow of time any less real as an experience. Pain is real, even though pain is constructed by the brain. Colors are real as experiences, even though the electromagnetic radiation that causes them is just wavelengths, not intrinsically colored. The flow of time is real as a feature of consciousness, even if it's not a feature of spacetime. And this leads us to the final piece of the puzzle: memory. Because the brain's construction of the present moment wouldn't give us a sense of flow by itself. For time to feel like it flows, we need not just a sense of now, but a sense of direction, a feeling that now is moving from past toward future, not the other way around. And that directionality comes from memory. Why do you remember yesterday, but not tomorrow? The question sounds absurd. Of course you remember yesterday. It happened, it's in the past, it's recorded in your brain. And of course you don't remember tomorrow. It hasn't happened yet. There's nothing to record. The asymmetry between past and future seems so obvious it barely needs explaining. But from the perspective of fundamental physics, where the laws are time-symmetric and work equally well forward and backward, this asymmetry is not obvious at all. Why should memory point in one direction of time and not the other? What makes the past accessible to memory, while the future isn't? The answer connects back to entropy and the second law of thermodynamics. Memory, as a physical process, requires creating correlations between your brain and external events. When you remember eating breakfast, what's actually in your brain is a pattern of neural connections that correlates with the event of eating breakfast. The neurons that were active during breakfast have strengthened their connections, creating a physical trace, a record of the event encoded in the structure of your brain. Creating this record requires energy. Neurons must fire, synapses must be modified, proteins must be synthesized. All of these processes generate heat, increase disorder at the molecular level, and raise the total entropy of the universe. So memory creation, like all physical processes, obeys the second law of thermodynamics. It increases entropy. Now here's the key insight. You can only create correlations with events that occur when the universe has lower entropy than it does now. This is because the direction of increasing entropy is the direction from past to future. Events in your past happened when entropy was lower. Events in your future will happen when entropy is higher. Your brain, as a thermodynamic system, can create records of lower entropy states because those states provide the organization, the structure, the information that gets encoded in memory. Think about a photograph, an actual physical photograph, not a digital one. You point a camera at a scene. Light from the scene exposes photographic film, and a chemical reaction creates a permanent record of the light pattern. This record is possible because the photographic film starts in a special prepared state, a low entropy state where the chemicals are arranged in a specific way. The light causes this organized state to change into a different organized state that preserves information about the light pattern. Crucially, this only works in one direction. You can't take an exposed photograph and shine light on it to produce the original scene. The process is irreversible, and it's irreversible because it increases entropy. The organized state of the unexposed film transforms into a differently organized state of the exposed film, but the total entropy of the film plus its environment increases. Your memory works the same way. Your brain starts each moment in a particular state, a relatively organized state shaped by evolution and development, and all your previous experiences. Events happen. Sensory information arrives, and this information causes your brain state to change in ways that preserve a record of the events. But this is an entropy-increasing process. You can't run it backward. You can't take a memory and use it to physically recreate the past event. This is why we remember the past and not the future. The past is in the direction of lower entropy, where the organized structures that become records can exist and persist. The future is in the direction of higher entropy, where those structures haven't formed yet, where there's nothing to record because the necessary organization doesn't exist. But wait, you might think, the future will have organized structures too. My brain will be in specific states tomorrow, next week, next year. Why can't I access those states now as memories of the future? The answer is that those future brain states don't exist yet, not in a way that can influence your present state. Remember the block universe picture, where all moments exist, together in space-time. In that picture, your future brain states do exist, at future temporal coordinates. But the causal structure of space-time only allows influences to propagate forward in time, from past to future, not backward. This one-way causation is itself a consequence of entropy. Causes precede effects because causal relationships create correlations, and correlations can only form in the direction of increasing entropy. So you can't remember the future because causal influences from the future can't reach your present brain state. And this isn't a limitation of your brain. It's a fundamental feature of how causality works in a universe where entropy increases. Stephen Hawking explored this connection between memory and entropy in A Brief History of Time. He pointed out that our ability to remember the past is intimately connected to the thermodynamic arrow of time. If entropy were decreasing instead of increasing, we would remember the future and not the past. Our sense that time flows forward is tied to the fact that entropy flows forward. Interestingly, this means that memory itself contributes to the arrow of time. Each time you form a new memory, you're creating correlations between your brain and the world, and these correlations represent an increase in the total information content of the universe. The physicist Seth Lloyd has argued that the arrow of time is fundamentally an arrow of increasing correlations. The universe started with its parts relatively uncorrelated, and as time goes on, more and more correlations form through causal interactions. Your memories are part of this process. Every memory you have represents a correlation between your present brain state and a past event. The accumulation of these correlations over your lifetime is what gives you a sense of personal history, of having a past that stretches behind you. And because new correlations keep forming, because you keep making new memories. You have a sense of moving forward through time, of the present moment always being new, never repeating. But here's something weird. Even though you can't remember the future, you can predict it. You can imagine tomorrow, plan for next week, anticipate future events. Isn't this a kind of future-directed cognition that mirrors past-directed memory? Yes and no. Prediction is different from memory in a crucial way. Memory is based on records, on physical traces of past events encoded in your brain. Prediction is based on models, on patterns you've extracted from past experiences that you project forward to anticipate what might happen. Predictions are not records of the future. They're constructions based on records of the past. When you predict that the sun will rise tomorrow, you're not accessing a record of tomorrow's sunrise. You're using your memory of all the previous sunrises you've seen, your understanding of how the Earth rotates, and your assumption that these patterns will continue. The prediction points toward the future, but it's made from past information. This asymmetry between memory and prediction is another aspect of the psychological arrow of time. The past feels different from the future, not just because we remember one and not the other, but because our relationship to them is fundamentally different. The past is fixed, determined, knowable through memory. The future is open, uncertain, knowable only through prediction and anticipation. This difference is real and important, even in a block universe where all moments exist. Why is it real? Because even though all moments exist in space-time, your access to them is asymmetric. You have direct causal contact with the past through the records it has left in your brain. You don't have direct causal contact with the future. You can only model it based on past patterns. This epistemic asymmetry, the difference in what you can know about past versus future, is grounded in the thermodynamic asymmetry of entropy increase. There's also the question of emotional and volitional asymmetry. We feel regret about the past, but hope for the future. We can't change the past, but we feel we can influence the future. These emotional and volitional attitudes also follow the arrow of entropy. We regret the past because it's fixed, recorded, unchangeable. We hope for the future because it's open, unpredictable, seemingly susceptible to our influence. But is the future really open? In the block universe, all moments exist, including all future moments. Your future actions exist at future temporal coordinates. Does this mean they're determined? That you can't actually change the future? This is the free will question, and it's deeply tied to the nature of time. If the future already exists, then in what sense is it open? If your future decisions are already out there in the block of space-time, then were they really decisions, or were they predetermined? One response is to say that already exists is the wrong phrase. The future exists at future times, not at the present time. To say it already exists is to smuggle in an illegitimate notion of absolute time, a universal now that we know doesn't exist. Your future decisions exist when you make them, in your future. Right now, in your present, they haven't been made yet. So they're still open, still undecided. Another response is to distinguish between determinism and fatalism. Determinism says that given the current state of the universe and the laws of physics, the future is uniquely determined. Fatalism says that the future is fixed regardless of what you do. Determinism might be true, but fatalism isn't. Your actions are part of what determines the future. So the future isn't fixed independent of your choices. It's fixed partially because of your choices. These philosophical debates are fascinating, but they don't change the basic experiential fact. You remember the past and not the future, and this asymmetry is grounded in the thermodynamic arrow of time. Your sense that time flows from past to future, that you're moving forward through moments, is constructed by your brain from this asymmetry. You experience time as flowing because you accumulate memories in one direction, because causes precede effects in one direction, because entropy increases in one direction. The psychological arrow of time is real and important. It's how conscious beings like us navigate a block universe where all moments exist, but we can only access them asymmetrically. We construct a flowing present from a static four-dimensional structure by combining our location in time with our memories of the past and our predictions of the future. The result is the vivid, undeniable experience that time passes, that we're moving forward through it, that the present moment is special and unique. This experience might be a construction, but it's not arbitrary. It's grounded in physics, in entropy, in causality, in the structure of spacetime. The flow of time is how the thermodynamic arrow appears to consciousness. It's how a brain embedded in a block universe makes sense of its place in that universe. And recognizing this helps us see why reconciling our experience of time with what physics tells us about time is so challenging. The experience and the physics are describing different aspects of reality. Physics describes the objective structure of space-time, where all moments exist and there's no flow. Experience describes the subjective structure of consciousness, where memory and prediction create a sense of flow from past through present to future. Both descriptions are true. The challenge is understanding how they fit together. We've covered a lot of ground. We've seen how relativity leads to the block universe, where all moments exist together and time doesn't flow. We've seen how entropy creates an arrow of time, giving events a preferred direction, even though the fundamental laws are time-symmetric. We've seen how quantum mechanics challenges our intuitions about time at the smallest scales. And we've seen how the brain constructs the experience of now, creating a sense of flow from the asymmetry of memory and causation. But for all this understanding, there remains a profound mystery: consciousness itself. Why does it feel like something to exist in time? Why is there a subjective experience of the present moment at all? Why does the flow of time have a vivid, qualitative character that seems irreducible to any physical description? This is what philosopher David Chalmers calls the hard problem of consciousness. We can explain how the brain processes information, how it creates memories, how it generates predictions. We can map the neural correlates of different conscious experiences. We can build increasingly sophisticated models of how cognitive processes work. But none of this explains why those processes feel like anything from the inside. Consider the experience of seeing the color red. Neuroscience can tell you which wavelengths of light trigger which photoreceptors in your retina, how that information gets processed in your visual cortex, how it's categorized and labeled and integrated with other information. But none of this explains the subjective quality of redness, the what it's like to see red that seems to be a fundamental part of the experience. The same applies to the experience of time. We can explain why you remember the past and not the future. We can explain how your brain creates a sense of now by binding together sensory information within a temporal window. We can explain why entropy increase creates a directional arrow. But we can't explain why the passage of time feels the way it does. Why there's a subjective flow, a sense of moving forward through moments, a vivid presence of now. Some philosophers and scientists think the hard problem is a genuine mystery that will require radically new kinds of explanations. Maybe consciousness is a fundamental feature of the universe, like mass or charge, not reducible to anything more basic. Maybe there are psychophysical laws that connect physical processes to subjective experiences, laws we haven't discovered yet because we've been looking in the wrong places. Others think the hard problem is a confusion, that once we fully understand the functional and computational aspects of consciousness, the subjective aspects will be explained as well. Maybe the feeling of flow is just what certain kinds of information processing feel like from the inside. Maybe asking why it feels like something is like asking why water is wet. It's not an additional mystery beyond understanding the molecular structure and dynamics. But wherever you stand on the hard problem, the experience of time poses special challenges, because unlike other conscious experiences, which are about things in the world, colors are about light, sounds are about pressure waves, pains are about tissue damage. The experience of time seems to be about the very structure of experience itself. Time isn't something you perceive like an object in the world. It's the framework within which all perception happens. You perceive objects in space and events in time, but you don't perceive time itself. You live through it, experience it, but from the inside, as the medium of consciousness rather than its content. This makes the experience of time particularly hard to explain in physical terms. You can imagine, at least in principle, building a robot that responds to red light the same way humans do, that categorizes it as red, that uses that information appropriately. Would the robot experience redness? Maybe, maybe not, but at least we can specify the functional requirements. But how would you specify the functional requirements for experiencing the flow of time? What would it mean for a system to genuinely experience temporal passage, as opposed to merely tracking temporal order? Some researchers think the answer might lie in the structure of consciousness over time. The philosopher of mind Thomas Metzinger has argued that the sense of self is a kind of simulation, a model the brain creates of itself as a unified subject of experience. Maybe the sense of time's flow is part of this simulation. The brain models itself as persisting through time, and this model includes a representation of temporal passage. Others point to the role of attention and working memory. Consciousness seems to have a limited capacity. You can only be aware of a few things at once. And consciousness seems to update continuously as new information arrives. Maybe the sense of flow comes from this updating process, from the way attention shifts and working memory gets refreshed moment by moment. The flow isn't in time itself. It's in the dynamics of conscious processing. There's also the possibility that the flow of time is related to the unity of consciousness, the fact that all your experiences at a given moment come together into a single, unified field of awareness. You don't have separate consciousnesses for vision and hearing and touch. you have one consciousness that includes all these modalities. This unity might require some kind of temporal integration, some process that binds together experiences occurring at slightly different times into a coherent whole, and that temporal binding might be what we experience as the flow of time. But these are all speculations. The truth is, we don't know why there's a subjective flow of time. We don't know why consciousness has this temporal dimension, this sense of moving from past through present to future. We don't even know if these questions are the right ones to ask. Part of the difficulty is that time is so basic to our experience that it's hard to step outside it and examine it objectively. When you try to study time perception, you're using mental processes that unfold in time to study time itself. It's like trying to see your own eyes without a mirror. The very tool you'd use to look is what you're trying to look at. There's also the question of whether the flow of time is unique to consciousness, or whether it's something physical systems could have more generally. Does a thermometer experience temperature? Does a clock experience time? Most people would say no. These are just physical processes, not conscious experiences. But where's the line? At what point does a physical process that tracks time become a conscious experience of time? We don't know. Some radical theories suggest that consciousness might be more fundamental than we think, that it might go all the way down to the quantum level or even beyond. In these theories, often called panpsychist theories, every physical system has some rudimentary form of experience, and complex consciousness like ours is what you get when you put together lots of simple experiences in the right way. If this were true, then the flow of time might be a basic feature of the universe that gets amplified and made vivid in conscious beings like us. Other theories suggest that consciousness might not be produced by the brain, but rather constrained by it. That the brain acts like a filter, selecting which aspects of a larger consciousness become accessible to us. In these theories, the flow of time might be something consciousness imposes on the timeless structure of reality, rather than something consciousness discovers in reality. These are fringe ideas, not mainstream science, but they illustrate how wide open the question of time and consciousness remains. We have good theories about the physics of time. We have increasing understanding of the neuroscience of time perception. But the connection between objective time and subjective time, between space-time and experience, between the block universe and the flowing present, that remains mysterious. Maybe future neuroscience will crack the problem. Maybe we'll discover the neural correlates of temporal experience, the specific brain processes that give rise to the sense of now and the feeling of flow. Maybe we'll be able to manipulate these processes, alter time perception at will, even create artificial systems that genuinely experience time the way we do. Or maybe the mystery will persist. Maybe consciousness and its temporal dimension will turn out to be something that can't be fully captured by third-person objective science. Maybe the first-person experience of time is fundamentally different from any description we could give of it from the outside. Either way, understanding time requires understanding both its objective and subjective aspects. The physics tells us about the structure of space-time, the mathematics of relativity, the thermodynamics of entropy. The phenomenology tells us about the experience of now, the feeling of flow, the asymmetry of memory and anticipation. These two perspectives need to be reconciled. and we're still figuring out how. What we do know is that time is stranger than it appears. The simple, straightforward flow from past through present to future that we experience every day is not how time works at the fundamental level. Time is relative, not absolute. It's part of space-time, not separate from it. All moments exist together, not sequentially. The flow we experience is constructed by our brains from thermodynamic asymmetry and neural dynamics, not given to us directly by reality. This doesn't make our experience false or illusory in a simple sense. Experience is real. The flow of time as an experience is as real as anything else, but it's a feature of consciousness, not a feature of the cosmos. And recognizing this helps us understand both what physics has discovered about time and what it hasn't yet been able to explain. So where does this leave us? We've journeyed through the physics of time, the thermodynamics of entropy, the quantum mysteries, the neuroscience of temporal perception, and the hard problem of consciousness. We've seen that time, as physics describes it, is radically different from time as we experience it. The block universe picture says all moments exist together, equally real, with no objective flow. But our experience insists that time flows, that the present is special, that there's a genuine difference between past and future. Can we live with this paradox? Can we accept both truths, the truth of physics and the truth of experience, without having to deny one to accept the other? I think we can, but it requires a shift in how we think about the relationship between reality and experience. We need to stop seeing them as competing descriptions of the same thing and start seeing them as complementary descriptions of different aspects of existence. Physics describes the objective structure of the universe, the view from nowhere, the mathematical relationships that hold regardless of any particular observer's perspective. From this view, space-time is a four-dimensional manifold where all events exist at the respective coordinates. There's no flow, no becoming, no privileged present moment. Time is just one dimension among four, woven together with space into a unified geometry. But you are not nowhere. You are somewhere, a particular observer, embedded in space-time at a particular location, with a particular history and a particular perspective. And from this embedded viewpoint, the four-dimensional block naturally gives rise to a three-dimensional space, evolving through one-dimensional time. Your consciousness, tracking through your world line, experiences moments sequentially, because that's what being a conscious observer in a block universe is like. The flow of time is how the block appears from inside. It's not an illusion in the sense of being false. It's a perspective, a way the objective structure manifests to subjective experience. Just as a sphere looks like a circle when you view it from a certain angle, the block universe looks like flowing time when you view it from a conscious perspective embedded in it. This doesn't make either picture less real. The sphere is really a sphere, not a circle. But the circle is really what you see when you look at it from that angle. The block universe is really a four-dimensional structure without flow. But the flowing time is really what you experience when you're a conscious being moving through that structure. What about free will and the openness of the future? If all moments exist in the block, including all your future decisions, does that mean everything is predetermined? Here's one way to think about it. Your decisions are real events in space-time. Just like any other events, they exist at their temporal coordinates, but they're not determined independently of you. They're determined partially by you. You, as a conscious agent, are part of what determines which future exists. The block includes your decisions because it includes you making those decisions. The future is fixed in the sense that there's a fact about what will happen, but it's not fixed independently of what you do. What you do is part of what fixes it. This is sometimes called compatibilism, the view that free will and determinism are compatible, because free will doesn't require that your actions be uncaused, just that they be caused by you, by your desires and deliberations and decisions. Whether this resolves the free will problem is debatable. Some people feel that if the future already exists, then their choices aren't truly free. That genuine freedom requires the future to be genuinely open, not yet determined. Others feel that as long as their choices flow from their own mental states and aren't externally forced, they're free enough, even if those choices exist at future temporal coordinates in the block. But regardless of where you stand on free will, the block universe doesn't have to be fatalistic or deterministic in a way that robs life of meaning. You still make choices. You still act. You still create your future through your decisions and efforts. The fact that all this exists from a temporal perspective doesn't change the reality of it from your temporal perspective. Similarly, the fact that time doesn't objectively flow doesn't mean your memories are false or your anticipations meaningless. Your past really happened to you in your past. Your future really will happen to you in your future. The asymmetry between past and future is real and grounded in thermodynamics. The flow you experience is a genuine feature of consciousness, even if it's not a feature of space-time. What this understanding does is free us from certain confusions and puzzles. We don't have to wonder why the present moment is special. It's not special objectively. It's just where you are right now. We don't have to worry about how the future can be simultaneously open and closed. It's open epistemically, you don't know it, and closed ontologically. It exists in the block. We don't have to reconcile the flowing time of experience with the static time of physics. They're describing different levels of reality, the subjective and the objective. This also gives us a new appreciation for the role of consciousness in the universe. If the flow of time is a feature of consciousness, then consciousness is doing something extraordinary. It's creating temporal flow from timeless structure, generating the experience of becoming from static being. Consciousness is how the universe comes to experience itself as dynamic and changing, even though the underlying reality might not be. Some find this comforting. It means that our experience, our inner life, our sense of moving through time, these aren't illusions to be dismissed, but real phenomena worthy of study and respect. The flow of time might not be in the physics, but it's in us, and we're part of the universe too. Others find it disturbing. It means that the flowing river of time we feel we're carried by doesn't exist outside our minds. It means that the special quality of the present moment, the sense that right now is uniquely real, is something we bring to the universe, rather than something we find in it. It means that in some deep sense, we're more alone than we thought, each of us creating our own personal flow through a static block. But perhaps there's a middle way. Perhaps the flow of time is neither purely subjective nor purely objective, but intersubjective, something that emerges when conscious beings interact, when we share our experiences and coordinate our actions. Perhaps the social construction of time, with its clocks and calendars and shared schedules, is what makes the flow of time a common reality rather than just an individual experience. After all, we all agree on the direction time flows. We all experience the same arrow from past to future. We all remember yesterday and anticipate tomorrow. This common direction grounds our shared reality, our ability to communicate and cooperate and build civilizations. The flow might be in our minds, but it's in all our minds in the same way. And that shared experience creates a kind of objective intersubjectivity. What's remarkable is that physics has revealed all this to us. A century ago, we thought time was absolute and universal, flowing the same for everyone everywhere. Now we know it's relative and local, different for different observers. We thought the present was objectively real, and the future was genuinely open. Now we understand that all moments exist together in the block of spacetime. We thought the flow of time was a basic feature of reality. Now we see that it emerges from entropy and consciousness. These discoveries haven't diminished time. They've deepened it. Time is more mysterious, more subtle, more intimately connected to the nature of the universe and the nature of mind than anyone imagined. Understanding time means understanding relativity and thermodynamics and quantum mechanics. But it also means understanding consciousness and experience and the subjective flow that makes us who we are. We live in a block universe that doesn't flow, but we experience a flowing time because we're conscious beings with memories and anticipations, embedded in a universe with an entropy gradient. Both descriptions are true. Both are needed to fully understand time, and both point to the profound strangeness and beauty of the cosmos we inhabit. The flow of time is real, but it doesn't flow the way you think. It flows in your experience, constructed by your brain from thermodynamic asymmetry and neural dynamics. It doesn't flow in space-time, which contains all moments together in a four-dimensional structure. And reconciling these truths, living with both the block universe and the flowing present, is part of what it means to be a conscious observer in this strange and wonderful universe. As you settle deeper into rest, your thoughts drifting and slowing, let this mystery sit with you gently. Time is not what it seems. The flow you feel so deeply, that movement from past through present into future, is a construction. Beautiful, useful, real as an experience, but not real as a fundamental feature of the cosmos. You are living in a four-dimensional block where all moments exist together, but you experience them sequentially because that's what consciousness does. It creates flow from structure, becoming from being, passage from stasis. This isn't troubling if you hold it lightly. Your memories are still real. Your experiences still matter. Your life still unfolds, still has meaning, still contains joy and sorrow and wonder. The fact that all of it exists together in the space-time block doesn't diminish any of it. If anything, it makes it more precious. Every moment you've lived, every person you've loved, every experience you've had is preserved forever in the eternal structure of space-time. Nothing is truly lost. Everything that was, is, and will be exists, crystallized in the four-dimensional geometry of the universe. And you, right now, in this moment, are part of that geometry. Your consciousness, moving through its world line, experiencing the flow of time, feeling the present moment as vivid and real and uniquely now. This is how the universe comes to know itself. This is how the block becomes alive, dynamic, meaningful. Through you, through your experience, through the flowing present that you construct from the timeless structure. So rest easy. Time may not flow the way you thought, but it still flows for you, in you, through you. And that's enough. That's everything. If you enjoyed exploring this mystery, please consider subscribing to the channel and liking this video. There's so much more to discover about the strange and beautiful nature of reality, and we'll be here, exploring it together, one moment at a time. Now let your eyes close, let your breathing slow and drift into sleep. The universe is vast and strange and wonderful, and you are part of it, experiencing it, giving it meaning through your consciousness. Rest well, knowing that every moment of your life is woven forever into the fabric of space-time, eternal and real and yours. Good night.